Welcome back to this series on neural network programming. In this video, we will visualize a tensor flatten operation for a grayscale image, and we'll show how we can flatten specific axes within a tensor. This type of selective flattening is often required because our tensors flow through our networks as batches, so we'll see how this is done. Without further ado, let's get started. A tensor flatten operation is a common operation inside convolutional neural networks because convolutional layer outputs that are passed to fully connected layers must be flattened out before the fully connected layer will accept them as input. In videos past, we learned about a tensor shape and then about reshaping operations and found that a flatten operation is a specific type of reshaping operation, whereby all the axes are smushed or squashed together. If we want to flatten a tensor, we need to have at least two axes. This makes it so that we are starting with something that's not already flat. Let's look now at a handwritten image of an 8 from the MNIST dataset. This image has two distinct dimensions, height and width. The height and width are 18 by 18 respectively. These dimensions allow us to know that this particular image has been cropped because the MNIST dataset contains 28 by 28 images. Let's see now how these two axes of height and width are flattened out into a single axis of length 324, which is 18 squared. And this is our flattened output with a single axis of length 324. The white on the edges corresponds to the white at the top and the bottom of the image. Each node in the fully connected layer receives this flattened output as input. In this particular example, we are flattening the entire image tensor. But what if we wanted to only flatten specific axes within this tensor? This is typically required when working with CNNs because we won't be dealing with just a single tensor. We'll be dealing with a tensor that is a batch that contains multiple images. I'm here in a notebook now, and let's see how we can flatten out axes of a tensor in code with PyTorch. In the video where we talked about CNN input tensor shape, we learned how tensor inputs to a convolutional neural network typically have four axes, one for the batch size, one for the color channels, and then one each for the height and width. Let's kick things off here by constructing a tensor to play around with that meets these specs. Suppose we have the following three tensors. Each of these has a shape of 4 by 4, so we have three rank 2 tensors. For our purposes here, we'll consider these to be three 4 by 4 images that we'll use to create a batch that can be passed to a CNN. Remember, a whole batch is represented using a single tensor, so we'll need to combine these three tensors into a single larger tensor that has three axes instead of two. In this code, we use the stack function to concatenate our sequence of three tensors along a new axis. Since we have three tensors along this new axis, we know the length of this new axis is 3. And indeed, we can see in the shape that we have three tensors that have a height and width of 4. The axis with a length of 3 represents the batch. The 3 tells us the batch size, while the axes of length 4 represent the height and width respectively. This is what the output for this tensor representation of a batch looks like. At this point, we have a rank 3 tensor that contains a batch of three 4 by 4 images. All we need to do now to get this tensor into a form that a CNN expects is add an axis for the color channels. We basically have an implicit single color channel for each of these image tensors. So in practice, these would be grayscale images. A CNN, however, will expect to see an explicit color channel axis. So let's add one by reshaping this tensor. Notice how we have specified an axis of length 1 right after the batch size axis. Then we follow with the height and width axes of 4 by 4. Also notice how the additional axis of length 1 doesn't change the number of elements in the tensor because the product of the components doesn't change when we multiply by 1. I'm here on the blog post for this video on DEEPLIZARD.com where I've formatted the output for this tensor so we can inspect it more easily. Let's look at each axis. The first axis has 3 elements. Each element of the first axis represents an image. For each image, we have a color channel axis which contains a single channel. And within each channel, we have 4 arrays that contain 4 numbers, or the scalar components of the tensor. That's the structure of this tensor. Let's have a look at this in code now by indexing into this tensor. We have the first image. We have the first color channel in the first image. We have the first row of pixels in the first color channel of the first image. We have the first pixel value in the first row of the first color channel of the first image. Alright, let's see how to flatten the images in this batch. Remember, the whole batch is a single tensor that will be passed to the CNN. So we don't want to flatten the whole thing. We only want to flatten the image tensors within the batch tensor. We'll start by flattening the whole thing first so we can see some of the solutions from the coding question in the last video. Mick, Amir, and thank you for providing these solutions. There'll also be another coding question in this video, so don't miss it. At the bottom, you'll notice that there's also another way that comes built in as a method for tensor objects called, you guessed it, flatten. This method produces the very same output as the other alternatives. What I want you to notice about this output is that we have flattened the entire batch, and this smashes all of the images together into a single axis. Remember, the 1s represent the pixels from the first image, the 2s from the second image, and the 3s from the third. This flattened batch won't work well inside our CNN because all of the images have been flattened into one, and we need individual predictions for each image in the batch. The solution here is to flatten each image while still maintaining the batch axis. This means we want to flatten only part of the tensor. We want to flatten the color channel axis with the height and width axes. This can be done with PyTorch's built-in flatten method. Notice how in the call we specified the start dim parameter. This tells the flatten method which axis it should start with when it begins the flatten operation. The 1 here is an index, so it's the second axis, which is the color channel axis. We skip over the batch axis, so to speak, leaving it intact. Checking the shape, we can see that we have a rank 2 tensor with 3 single color channel images that have been flattened out into a single axis containing 16 pixel values for each image. In this example, we use the built-in flatten method to achieve these results. Here's the coding challenge for this video. How can the same results be achieved by reshaping the batch tensor using the reshape method directly? Let us know your answer in the comments, and take a shot at it before looking at any of the other comments. It's not a big deal if you think of the same solution as someone else. Give a thumbs up to let us know you're learning. If reading's your thing, check out the blog post for this video on DEEPLIZARD.com, and also check out the DEEPLIZARD HiveMind where you can get exclusive perks and rewards. Thanks for contributing to collective intelligence. I'll see you in the next one.
10 years ago, computer vision researchers thought that getting a computer to tell the difference between a cat and a dog would be almost impossible, even with a significant advance in the state of artificial intelligence. Now we can do it at a level greater than 99% accuracy. This is called image classification. Given an image, put a label to that image. I work on a problem called object detection, where we look at an image and try to find all of the objects, put bounding boxes around them, and say what those objects are. So it smoothly tracks me as I move around the frame, and it's robust to a wide variety of changes in size, pose, forward, backward. This is great. This is what we really need if we're going to build systems on top of computer vision. And I'm really excited because now we have a pretty powerful solution to this low-level computer vision problem, and anyone can take it and build something with it. So now the rest is up to all of you and people around the world with access to this software, and I can't wait to see what people will build with this technology. Thank you.